Hello everyone, and thank you for taking the time to watch our presentation on Localized Semantic Feature Mixers, or LSFM. The problem with current state-of-the-art AI detectors is that they suffer from long inference times and decreased capability in the case of small, obstructed, or far-away pedestrians. Additionally, they struggle to handle the motion blur caused by vehicle movement. Our solution is the proposed LSFM architecture from Khan et al., utilizing multi-layer perceptron mixers, super pyramid pixel pooling, and the dense focal detection network. Current pedestrian detectors are generally based on vision transformers. Vision transformer, VIT, uses a method of processing called self-attention that basically determines what inputs need to be weighted with more importance. This process is effective, but it considers the inputs as a whole, which can be a huge amount of data to interpret at high resolutions. Multi-layer perceptron mixers still use a similar process, but it is performed simultaneously on smaller chunks of input, independent of the larger context and resolution. This makes scaling easy and efficient. The typical AI detectors use feature maps in a feature pyramid network. A feature map is the layout of the input data. The feature pyramid network, or FPN, produces feature maps from inputs at all sorts of different resolutions, scales them to uniform, then merges them. This process of upscaling or downscaling takes a lot of time and work to process. Here are a couple of pictures to do with the process itself. The left image is an example of what an AI pedestrian detector looks like in operation. You can see how, from the flattened perception of a camera, it can be difficult to identify people from even a short distance away, let alone ones that are partially obstructed. The image on the right shows the detector's process of identification in stages. You can see how it distills the features with each pass.
How LSFM works in comparison to the typical FPN is a simple pixel pyramid pooling, which takes the feature maps and it breaks them down into equally sized pixels, then builds a larger array out of those said pixels. You can see nothing has to be scaled since each map is broken down into uniform pieces. The dense focal detection network then interprets this information in patches and it makes it resolution independent. This is far more efficient. The graph above shows the performance over time for the different AI architectures in two different conditions, reasonable and heavy occluded. As you can see, LSFM beats each one of these on 3 different datasets, even beating Caltech on the human baseline. To work more efficiently under occluded conditions, LSFM is trained on a wide set with simulated obstruction and motion blur. It achieves this capability of detection, all while cutting the inference time by 55% on average. Making this local on the map, there's an amount of accidents on the intersection of Cobb Parkway and Barrett Parkway and the intersections of Old Highway 41 and Barrett Parkway. This map is from Georgia DOT, and the filters are specifically for these intersection collisions over the years of 2020 and 2022. This demonstrates how much of an impact with places that have pedestrian accidents have incidences. In the area between the intersections, there's barely any in comparison. Seeing how this is the more recent years and there's still this many accidents throughout it, a new sensor would be best to be able to decrease that number effectively.
Yeah, so the average auto accident settlement is about 20,237 per year. And taking into account all the AA accidents in the Barrett Parkway example, this would total for around 2.5 million for the 2020-2022 year time span. However, with this architecture implemented, it would reduce the amount of accidents by half due to the interference time, and would be around 44 accidents, which is about 1.25 million for the 2-year time frame. And the architecture has limited contextual understanding, and they operate on fixed size input sequences, will struggle in understanding long range dependencies or capturing contextual information effectively. This, yeah, and it was, yeah, of course, this is explaining the math from before, so yeah. Yeah, so these are our sources. Thank you all for taking the time to watch our presentation. Goodbye.